Hi guys, welcome back to the Astro Imaging channel. Tonight's session is on exoplanet observing by amateur astronomers, and our presenter is Dennis Conti. But as always, before we go into that, I'm going to jump over and share our image of the week, and you're going to see my full screen for a sec while I jump over. This week's image of the week is Andy Armoli's IFN around Polaris, and yes, there's IFN up there. Andy, I did send you out an invite to this session. If you got it, if you didn't get it, contact me midweek or something, and we'll have you come on next week and chat about this if you'd like. Really cool image, and this is one of those things that you could talk about for a while. It's a little bit more difficult to shoot, but great image, and don't guys, don't just look at it here. Go on the channel, click it, make it real big, and see a nice sized image of it. But thanks guys for submitting, and remember you can always submit. Check us out on Google Plus or Facebook is where we're taking some of the other submissions, or you could just share your image with the Astro Imaging channel. Just send a message over to the Astro Imaging channel with your image in it, and then you're up for consideration. But let me find my window here. But without any further ado, if I can click the right thing here, I'm going to send it right over to, well, I'm going to send it over to Dennis in a second, but I do want to remind you guys, wow, lots of people in the room already. I do want to remind you guys our Q&A is enabled, so if you have any questions for Dennis, he says just call him out to me and type them into Q&A, and I'll call him right out, and he'll answer them. But right now I'm going to hand it right over to Dennis. Dennis, there you go.
Okay. Can you see me okay, Adam? And hear me okay?
Fine. Yes.
Okay. All right. Well, welcome everybody. I'm here in cloudy Maryland. I don't think I've seen a clear sky in probably in about a month. So there's no difference tonight. What I will be doing is a presentation on exoplanet observing by amateur astronomers. And before I begin, let me just let everybody know that the presentation itself is available on my website at astrodennis.com. That's with two N's, astrodennis, all one word, .com. Also on that website is a link to a guide that I've put together, and it's called A Practical Guide on Exoplanet Observing. And it's designed for any of you folks who have been doing deep sky imaging or variable star observing as a way of transitioning into doing exoplanet observations. So with that, let me go ahead and see if I can successfully bring up my screen share here. And let me see if, Adam, can you see the slide here?
You're right there. Perfect.
Okay. All right. So the goal of my presentation this evening is really to show you how amateur astronomers can observe and detect, let me just say detect, exoplanets, and to be able to do so with incredible accuracy. The other point I want to make here in the presentation is that it can be done with the same equipment that is used for deep sky imaging, and we'll say a little bit more about that. And thirdly, that us amateur astronomers can materially contribute to exoplanet research, and I'll give some examples of that as well. If you look up at the night sky and you look at all the thousands of stars that you can see with your naked eye, the question is, which of them host one or more planets? Well, the answer is most of them, and in fact, amateur astronomers believe that 1 in 5 are actually believed to host a planet of roughly the same size of Earth that are in the so-called habitable zone that could support life. This particular star that this arrow is pointing to is in fact one that I've done a case study for of an actual exoplanet transit. And if we have time in the presentation, we'll actually go through that case study. Just a very quick review. Exoplanet, of course, stands for extrasolar planet. That is to say, a planet orbiting a distant star, which we'll call a host star. The first exoplanet was discovered back in 1992. And most exoplanets, just in terms of numbers, have been detected by Kepler, which I'm sure most of you have heard of and are aware of, as well as some ground-based observatories. However, the methods for actually detecting exoplanets vary. There are currently over 3,200 confirmed exoplanets. A week ago, or I should say about a week and a half ago, that number was 1,900. And so in the last week and a half or so, 1,300 have been added as confirmed Kepler exoplanets. So that number has jumped up dramatically in the last couple of weeks. There's a whole number of other candidate exoplanets. We'll talk about that in a minute. However, if I look at the methods that are used to detect exoplanets, some of which are used by amateur astronomers, the dominant one is the so-called transit method, and that's the one that we'll focus on for much of the presentation. And I'll be going over some examples of each of these right after this slide. The second dominant one is the so-called radio velocity method. Microlensing, again, we'll say a little bit more about these. Direct observation, that is to be able to actually see the exoplanet as distinct from its host star. The other three, the transit method, the radio velocity, and the microlensing methods, are more indirect methods. That is to say, we're not actually looking at the planet itself as an image, but we're actually looking at its effects in terms of effects on light or effects on spectrum. And there's a variety of other methods. So the dominant method, which is the transit method, is very simply the exoplanet as it's orbiting its host star. There will be a dip in light of the star, and that dip in light can vary from 1% to thousandths of a percent. Now, if you imagine, however, how this is possible, this particular transit method, of course, is only possible if the orbit of the exoplanet is in our direct line of sight. If the exoplanet is orbiting around the host star, that's to say not in our direct line of sight, then obviously it's not blocking the light from our point of view. So number one, it has to be an exoplanet orbiting within a very small number of degrees from our line of sight, and also a fairly large close-in exoplanet, which we call a hot Jupiter, obviously because it's close, namely hot, and Jupiter because it's of a size comparable to Jupiter. So those are the conditions that we're talking about for the transit method. In our line of sight, a close-in star, and about the size of Jupiter. What you see at the bottom of this little graphic here is in fact an actual light curve of the exoplanet that you saw that blinking arrow pointed to. And again, if we have time, we'll actually go through the case study, but you can see the dip in the light curve. Those little dots represent observations that were done of the brightness, or I should say the relative change in brightness of the host star. So this is the method that we'll come back to, but let's talk about a couple of the other methods. The second most popular method is the so-called radio velocity method. If you recall from your high school physics, any two bodies of mass are mutually attracting each other and have a common center of gravity. So if you look at a host star and a planet orbiting around it, there's actually a slight wobble to the host star caused by the planet going around it. Now in this case, the planet is not in our line of sight, but rather it's orbiting around the host star. that slight wobble in the host star, from our point of view, is causing a slight change in the spectrum of that host star, namely a Doppler shift. And based upon the change in spectrum, one can determine the radial velocity that is occurring from the point of view of the host star and us. And from that radial velocity measurement, one can determine certain characteristics of the exoplanet, in particular its mass. So there's some things that one can get with the radial velocity method that one cannot get with the transit method. Another pretty cool thing about the radial velocity method is something called the Rossiter-McLaughlin effect. And let me just say a few words about that. I think it's a pretty cool thing that happens here. As the host star is actually changing and rotating itself with a change in the spectrum in a blue shift and red shift that's occurring. If you look at the graphic down at the bottom, as the planet is transiting directly across the bottom of the host star, there's a little characteristic little curve, change in the curve of the brightness, or I should say of the spectrum of the host star. And that's because the planet first blocks the blue shift and then it blocks the red shift. So it's as if the blue shift went away and then it's as if the red shift went away. So from that little change in the light curve, one can actually determine the inclination of the orbital axis of the planet relative to the spin axis of the host star. And what you see here are three different curves of that change in light. So just by observing that little change in the light curve, one can actually determine the inclination of the orbit of the exoplanet relative to the spin axis of the host star. And furthermore, if that little dip is actually in reverse, one can actually determine that the planet is in a retrograde orbit relative to the host star. Namely, its orbit is opposite to the spin axis of the host star. Now, in doing this particular kind of method, the radial velocity method by amateur astronomers, it requires a fairly precise spectrograph. There have been some cases, just a very few cases, where amateur astronomers have been able to do the radial velocity method based upon a high precision spectrograph. The third method is the microlensing method. If you recall from having seen some Hubble photographs of a lensing effect, gravitational lensing effect by a foreground galaxy that magnifies and acts as a lens of a background galaxy, the same thing is happening here. What we're looking at here, however, is the curve, the light curve of a background star if you're looking into the middle of the Milky Way. And if you imagine in one of the arms of the Milky Way, if a planetary system moves in front of that background star, that planetary system will act as a lens and magnify, just as a gravitational lens would, magnify the light of the background star. And that's what you see in this graph here. But in addition, as that foreground planetary system has moved in front of the background star, when the exoplanet itself transits the star, there's going to be another little dip in the light curve. So this microlensing method is actually looking at the change in light, not of the host star, but rather of the background star that is being lensed by the foreground planetary system. Let me just kind of stop there, and Adam, just see if there's any questions that have come up before we move to the last method or so.
There aren't any new questions, but I'll remind you guys, Q&A, type in your questions and I'll call them out.
Okay, great. All right, so let me move on then. Um, the holy grail really of all the methods, of course, would be able to directly image an exoplanet. And you know, the analogy here is trying to view a candle next to a lighthouse, which with the bright star and a very dim exoplanet next to it. It has been possible from ground-based observatories to actually directly image an exoplanet using chronographs, but you can imagine how difficult it would be for amateur astronomers. I'm going to come back to this because I'm optimistic that just like with where we have come as amateur astronomers in a number of other areas, I'm optimistic there's going to be some breakthroughs here, and I'm going to talk about some technologies a little bit later as to why I think that's true. But this is obviously very tough to do, but it is one of the areas of exoplanet research that, of course, would have a great payoff if we're able to actually image an exoplanet and look at some characteristics of its atmosphere. So all of the other methods up to this point are indirect methods. We're just looking at changes in light. The direct imaging, of course, would be as I say, the holy grail of all of them. Okay, well, where are we with exoplanet observing? If you look at this graphic, we're looking down on top of the Milky Way, and our solar system identified there. That cone is Kepler observations, and the small concentric circle or ring around the solar system are ground-based observations. With the little white dots going to the middle of the Milky Way, some of the microlensing. So as you can see from this perspective, we've only really begun looking at exoplanets in our immediate neighborhood. Now, a slightly different perspective is, again, looking at the cone that Kepler has searched. It's only within the Orion spur that Kepler has looked at. Now, there have been some, because of a fault with Kepler, it is now looking at a different perspective along the ecliptic, but for the most part, the original Kepler observations were in this cone. So the point of all of this is that we've confirmed over 3,200 exoplanets just within this small neighborhood around our solar system. You multiply that, and this, by the way, for the most part, are those that are in our direct line of sight. So you can imagine the number of exoplanets that are not only in our Milky Way galaxy, but multiply that by the billions of galaxies, and the probability that there are exoplanets within the habitable zone is, truly incredible. So that's the point I want to make here, is that we've only really begun looking at exoplanets in our immediate neighborhood. Okay, so let's move back to the transit method, which is the dominant method that amateur astronomers use. And again, back to our little example here. Again, these are actual observations I took from my backyard observatory here in Annapolis, Maryland. And if you look at a light curve, there's a few important characteristics about it. There's the duration of the light curve itself, and there's the depth, and there's also the sort of characteristic sort of hump in the light curve itself. And from these very simple characteristics that amateur astronomers can make, one can derive amazingly the radius of the exoplanet, the radius of its orbit, and the inclination of the exoplanet with our line of sight. And you'll see a little bit later in the case study, these can be done with 90% plus accuracy relative to professional published data on these exoplanets. I should say that the types of observations that amateur astronomers are doing are really fall into three categories. One is to confirm candidate exoplanets as being truly exoplanets. The second is to refine the ephemeris of an existing and known exoplanet. And by refining the ephemeris, what we mean by that is giving the professional astronomers an up-to-date idea, for example, of where the center point is of the dip in light, and that will help them with some of their other research, and I'll talk about that later. And the third thing that amateur astronomers are doing are actually discovering new exoplanets. There's actually some small number of amateur astronomers who are conducting their own sky surveys to try to detect new exoplanets that haven't been detected and confirmed by some of the professional surveys that are out there. Okay, so how do we create this light curve? Well, the key is using something called differential photometry, which has been around for a while for folks who've been doing variable star observing. And very simply, it's calculating the relative change, and relative is the important word here, relative change in flux between the host star and one or more comparison stars. So let's say, for example, we have a candidate host star that we think might have an exoplanet around it. We take images of that host star, looking at measuring basically the flux of that host star, and at the same time, in the same field of view, we take flux measurements of comparison stars around it. Now, why are we doing that, and why are we not just measuring the change in flux of the host star? Well, very simply, from us ground-based observers, you can imagine that if we're looking at just the brightness of an individual star, and let's say a passing thin cloud moves overhead, there'll be a change in brightness of that host star, and we're not able to determine, if we're just looking at the brightness of the host star, whether that's indeed a transit or whether it's something else. So the reason for doing the comparison stars is that theoretically, if there's a, let's say, thin passing cloud going over, that both the host star and the comparison stars will drop in light, in brightness and flux, relatively the same. So as they're going up and down in brightness and light, if we see a change to the host star but not the comparison stars, then more than likely that's indicative of something uniquely happening around the host star. And so that's why the word relative is important here, is we're looking at the relative change between the host star and the comparison stars. Now, that flux change can be due to a number of things, and that's not only just passing clouds, but light pollution, sky glow, moonlight, and so on. So in measuring this relative change, we then plot basically the data points of that change in flux. And if we see a sort of characteristic drop in light and then sort of a bucket sort of shaped curve, we then apply a model to those data points and see how well that model of what a typical transit should look like, how well that model fits to those data points. And then that tells us a measure of the quality of our observation. If that transit model, let's say, has a RMS that indicates a pretty tight fit, then that says we've got a pretty good observation. So this is these are the techniques used for actually coming out with that light curve that you saw in the previous slide. Now, the other interesting thing that one can observe is the possibility, for example, of that planet passing in front of a star spot. So if you can imagine that if there's a star spot, let's say a fairly large one, on the host star, and a planet moves in front of it, what is going to appear to have happened is that that planet has sort of disappeared. Namely, what's going to happen is there's going to be a slight bump in the light curve, as you sort of see to the left of the center line here of this particular plot. And so observing the light curve during the transit can also tell us if there's a star spot, or in fact if there's a flare. So if there's a flare that would occur, all of a sudden there's a brightening of the host star during the transit, one would also see that there would be a change in the light curve. So in addition to the transit itself, it's possible to also pick up some information about the activity of the star.
Dennis, can I interrupt you for 1 sec?
Sure.
I think at least someone is trying to ask a question, and they don't know where to ask a question. I don't think we've ever done this before, but I actually have a good way to show you where to ask your questions. I have, let's see, can you see it? Yeah, so this is, if you're watching on Google Hangouts, there's my computer screen, and that little box, let me see, that little thing right there, you click that, and it shows you Showcase and Q&A. You want Q&A, you hit Q&A, and it's going to, let's see, let me do that one more time. You hit Q&A, and it gives you that box right there to ask your questions. And then you can ask your question right at the bottom there. So hopefully that explains it. I know we haven't shown it with very descriptively in the past, so hopefully that's enough. And oh, look at that, a question's coming in from inside the room. Let me, oops, it disappeared on me. Hold on, I'm going to get to it in 1 second. What did the light curve look like last Monday when Mercury transited our star? Oh, okay. Not an exoplanet, but he has to ask.
Yeah, I would say, interesting the question is asked. I would say very, very obviously small dip in light for a couple of reasons. One is Mercury is not close and it's small. And now an interesting question would be, could a let's just call him an amateur astronomer be able to detect the transit of Mercury across our sun? I suppose theoretically, if it's in their line of sight and they had a fairly large aperture scope and all the rest, maybe. But my bet would be that if we were looking at, with the technology we have, a transit of something like Mercury, as small as it is, I would say it'd be pretty tough to see. Any other questions, Adam, before I go on?
Okay, yep, here they come. What kind of exposure length when using a DSLR, and should the image be slightly defocused to spread the stars over more pixels?
Okay, very good question. First of all, in terms of exposure times, it varies pretty much because the brightness of the stars, at least us amateur astronomers have been looking at, range from magnitude 8 to magnitude like 13. So depending upon what host star, I've taken observations, upwards of exposures anywhere from 30 seconds to 4 minutes. Now, as far as defocusing, actually a very interesting concept with exoplanet observing, unlike deep sky imaging, is since all that we're interested is collecting photons, it is true that in some cases with bright stars, a technique, in fact, is to defocus so that those photons are spread over multiple pixels. And then in the differential photometry, what we do is we capture around that defocused image or that defocused point spread function to get the photon. So defocusing is in fact a good technique for bright stars. But as far as the exposure time, it depends very much on the particular host star. except defocusing does have its limits in that you don't want to defocus too much. Otherwise, you could be spreading out into a close-in star, which is going to affect artificially the light curve. Any other questions, Adam, before I move on?
Yes. One more question. Are amateur astronomers meant more to help confirm exoplanets rather than to discover them?
The answer is yes. Actually, as I mentioned, there's three reasons the amateur astronomers are involved. One is to confirm candidate exoplanets. The second one, as I mentioned, is to observe known exoplanets to help refine the ephemeris. That's to say, the point in time where the transit is taking place. Any other questions, Adam?
All caught up with the questions, but keep
Okay.
asking them, guys.
Adam, I have one question. What's the typical observation period to make a transit observation?
So the question, what's the typical observation time? The transits themselves range from about 2 to 4 hours, but what we like to do is to get a baseline of 1 hour before and 1 hour after. So that would suggest that the observing session would range from 4 to 6 hours. And in fact, one of the things I was going to mention later, but I'll mention it now since it came up, is that those of us with German equatorial mounts where it might be necessary to do a meridian flip, which is highly possible for these long transits, where we then have to get back into that same field of view quickly and accurately, is a bit of a challenge. And in fact, I'll talk a little bit about it later. That suggests the importance, very much the importance of flat fielding, because the stars will end up on a different part of the CCD detector after the flip occurs, and that might artificially cause a change in the light curve itself.
I'm sorry, I had one more quick question. Is it possible to review historical data to find these exoplanets?
Is it possible to review historical data? It depends upon how historical. If you're talking about going back to old photographic plates, probably not. But in terms of going back to historical data, I would think that would be tough, because you can imagine what we're trying to do here is to look at a given star for 6 hours and collecting high precision photometry of it. And unless one is doing that specifically to look at exoplanets, unless you're talking about some of the large sky surveys that are, quote, historical, I think
No, actually, I was talking about some of the imaging that we do, like the luminosity, where you get 6-7 hours of luminosity data over 3 or 4 nights.
Oh yeah, if the equivalent of what you're doing is, well, if it's within a given night, you're getting 6 hours, then yes. But if it's spread over, 6 hours is spread over 4 or 5 nights, then probably not. Any other questions, Adam?
I'm going to save my questions till the end. So
Okay. All right.
go ahead.
Okay, so let me move on. So the point here is that amateur astronomers can detect exoplanets using predominantly the transit method. If we have time later, we'll see in the case study using the same equipment as deep sky imaging. Even in light polluted skies, here in Annapolis, Maryland, which is, I'm sort of in the suburbs here, the skies are, not great, but have been able to do some enough of good observations that have been able to contribute to some of the research scientists. And as I said earlier, with over 90% accuracy, and again, being able to provide these to professional astronomers for some of their research. Now, on that last point, if we look at, I'm going to talk about a couple of collaborations that are actually ongoing right now, that those of you out there who are doing deep sky imaging, if you're interested in getting involved in any of these, please shoot me an email and I'll get you hooked up with how to do some of these. So we have going on right now both observations from space platforms such as Kepler and ground-based observatories. There's a number of sky surveys being done by ground-based telescopes in both the northern and southern hemisphere. And we have amateur astronomers that are supporting both space-based and ground-based observatories in terms of, again, confirming candidate exoplanets or of refining the ephemeris. And let me talk about a couple of them. One that's been around for a few years is the so-called KELT follow-up project. KELT stands for Kilodegree Extremely Little Telescope, which, as the name implies, is what it says, which is relatively small aperture, but with a wide field of view. There's Northern Telescope and Southern Telescope. These are sky surveys that are done. What KELT does is to look at, in that field of view, around different targets, a change in light, and then amateur astronomers and other ground-based observers go back and look at those candidate exoplanets to confirm that, in fact, a transit has occurred. The reason for that is because a drop in light could also be due to an eclipsing binary. That is to say, two stars that are orbiting each other. So one star going in front of the other is going to cause a drop in light. And so there are methods for looking at a transit such as that to distinguish eclipsing binaries from eclipsing exoplanets. And so what the KELT project is doing is, in fact, making that distinction for any candidates. And then once those candidates have been confirmed using photometry, such as I described earlier, then those transits are further confirmed by radial velocity studies and other methods. So the KELT project is one that amateur astronomers are involved in of confirming possible exoplanets. The second one that I'm heading up, a worldwide network of amateur astronomers, is involved with a Hubble study that is taking place this year, looking at some 15 exoplanets. And in particular, here the professional astronomers are looking at those exoplanets with respect to their atmospheres. And I'm going to talk more about that on the next slide. The last one, which is relatively new, is not so much looking at exoplanets, but actually being able to help professional astronomers characterize so-called planetesimals. That's to say, let's say captured asteroids that are orbiting a host star that are breaking up, or other objects that are orbiting the host star that, again, cause a drop in light of the host star. And we'll give some examples of this as well. So let me say a few words about this Hubble study, because it's one that is actively taking place. And what this involves is the Hubble Space Telescope is looking at, in this year, 2016, 15 exoplanets. And the purpose of this HST study is, in fact, to characterize the atmosphere of these exoplanets relative to things such as the size of the planet, the characteristic of the star, and so on, so that when the James Webb Space Telescope is launched in a couple of years, that we'll have a better handle on what exoplanets, what host stars to focus on. The principal investigator is Drake Deming. Drake is currently a research scientist at the University of Maryland. He previously headed up the Planetary Science Division of NASA. The approach that Hubble is using is they're using their near-infrared camera, wide field camera 3, and they're looking at the spectrum and the near-infrared wavelength, in particular at the 1.4 micron band, which is the wavelength that is indicative of water being absorbed by the exoplanet. So as the exoplanet is moving in front of the host star, the light from the host star passing through the atmosphere of the exoplanet produces a change in spectrum of the host star. And then based upon that change in spectrum, in particular looking at this particular 1.4 micron band, they can determine some characteristics of the atmosphere of the exoplanet. So again, it's not looking at the atmosphere itself of the exoplanet, but rather it's looking at its effect on the change in spectrum of the host star. Now, the other interesting thing that Hubble is doing, the earlier question about defocusing the star for us ground-based observers that might be looking at bright stars, Hubble has the same problem. If they're looking at a bright star, they can't look at it for very long because, you know, their camera is going to get saturated. So the approach that is used here is something called spatial scanning, where as Hubble is actually looking at a host star, it's actually moving the camera, spreading the light across multiple pixels. It's as if you turned off your guiding on your scope and saw a star trail. Again, because we're not interested in pinpoint stars, we're just interested in collecting photons. This is a perfectly acceptable method that Hubble is using for counting photons of the host star. So that's the approach that Hubble is using, and each planet is being visited one or more times. Currently, we're about halfway through the year, and so we have already done about 9 exoplanet observations. The cool thing about this that amateur astronomers are doing is we're helping to refine the ephemeris. So the pipeline is that we do a number of full transit observations. I personally take a look at each one, reprocess them if necessary, pass them along to a fellow named Joey Rodriguez of the KELP team. He then does a global fit where he takes all of the good transits, combines them into one fit, and basically comes up with a refined ephemeris that is then passed to the Hubble team. The interesting thing about not only this project, but the KELP project, I should mention for those of you who are interested in this sort of thing, is that if your data is used by the Hubble Research Science team and is in fact in a is to be used in a published paper, you will be named as a co-author. And so already with the Hubble survey being done already, there have been a number of amateur astronomers, some of whom I know are on this call, that are going to be named as co-authors on some of these research science papers, which is pretty cool for amateur astronomers who really want to show that they really are contributing to science. Adam, let me stop at this point and just see if there's any other questions.
There aren't any new ones, but I'm going to wait until the end for mine because you may answer them, but.
Okay, all right, well, I'll keep going. Interrupt me if there are any that do come in.
Will do.
Okay, so the objective, I think I mentioned most of this. We're refining the ephemeris with the Hubble team. We've actually been asked to look at the activity of some select stars to determine if there's any star spots or flares. And these observations are done not at the time of transit, but rather so-called out-of-transit times. And at the bottom you see the status, as I said, 9 of the 15 exoplanets we've already made some observations of, and we'll be doing the remaining throughout the rest of this year. Uh, the reason for having a worldwide network of amateur astronomers for this Hubble project is because obviously at certain times transits are occurring that are not visible, let's say in North America, but they are in Europe, or they're not observable at all in the northern hemisphere, but they are in the southern hemisphere. So what you see here is a list of over 50 amateur astronomers involved in this network. I send observation notices out about every 1 or 2 weeks, giving everybody an update on what should be the targets to be looked at. We're fortunate now to have a site. One of our amateur astronomers has a remote observing site in the Atacama Desert. So we've got some southern sites as well in Australia, Cook Islands, and so on. A lot of sites in Europe, and some are coming up actually now in the Middle East. So we've got some good coverage. So just about every one of those exoplanets we're able to get some observations done. And in fact, we now have, for some of the observations, a collection from around the globe that are combined into this global fit for some of the ones already completed. Okay, well, so that's what we're doing with exoplanets. But more recently, there's been in the last, I'd say, 6 months, an incredible interest in amateur astronomers being involved in other than exoplanets, which I'm calling exo-objects. For example, disintegrating asteroids, so-called planetesimals, going around distant stars. There was a particular, let me back up a second. There was a particular star observed that had a very interesting light curve by Kepler. And this was back in the fall of last year. And professional astronomers looked at that light curve and realized that it's not an exoplanet, but it's something else. That then caused a series of observations by both professional and amateur astronomers. And what they determined is that it's some kind of object or objects now determined to be disintegrating asteroids or planetesimals that are breaking up around the host star. One of the amateur astronomers that has recently collected these light curves, in fact, I believe he's actually on the call here, is Mario Mata. And what you see here is a observation March 30th. And what you see between the two dotted lines is Mario's observation of WD 1145. This is that particular star I was referring to that was observed originally by Kepler to cause this strange light curve. And what you see in that gap between predicted times is this crazy light curve, which is indicative of a couple of objects that are transiting across the host star. Now, what I'm going to do is sequence through a number of observations that Mario did from March 30th, and you can see how the shape of that curve changes. So this is March 30th. This is April 6th, so just about 6 or 7 days later. And again, you can see that not only has during the transit, the curve changed, but also out of transit, the light curve has changed itself. So this is April 6th. This is April 12th. Again, a change in the light curve. This is April 16th, and it kind of looks like, it's sort of gone away, and you've got this sort of wider band around the host star. This is April 17th. Looks like it's gone away. But then this is May 10th. And again, a drop in light of the curve. So Mario is working with a research scientist at Harvard, in fact, who's I think one of the lead investigators on this, using Mario's data and some data from professional observatories to try to figure out what's happening. This is the very first time such a object of this nature has been observed. And obviously, if it's happening on one star, it's probably happening on a whole lot of other stars. So this opens up a whole different avenue for amateur astronomers to be involved in doing research. Now, Mario is fortunate in that he has a pretty good sized telescope. It turns out that on one of the days with my measly 11-inch scope, this is Mario's 32-inch scope, 1 minute exposure. That same night, this is with my measly 11-inch scope with an 8-minute exposure. And the point here is that, you know, with a modest size aperture, one can still see the signature of a bizarre sort of thing happening with a planetesimal. So the point of this is that it's great to have, you know, large aperture scopes to do this kind of high precision work, but the point is that even with modest size scopes, one can still see transits. Now, if you look at the depth of this transit, what's amazing is, you know, we're looking at going from like 0.6 to 1.1, so it's a pretty huge dip in light, and that kind of makes it easy as opposed to some of the exoplanet transits that are down in the, you know, 0.005 magnitude drop, which is still possible, but in some cases tough to do with modest size scopes. So I wanted to point this out as another avenue for amateur astronomers to get involved in. Now, where are we going with exoplanet observing from a professional point of view, and how can amateur astronomers help out? Well, we're looking at now beyond Kepler. TESS is a exoplanet survey that is the follow-on to Kepler that will be launched is scheduled to be launched in the fall of next year. TESS is going to have a much wider coverage than Kepler. If you recall that sort of cone of observations that Kepler had, TESS is going to be almost sort of an all-sky kind of survey. So what TESS is going to mean to us amateur astronomers is there's going to be a heck of a lot more follow-up observations that are needed. And what we're doing at the AAVSO, in fact, is trying to get ready for that by putting together a database of exoplanet observations, or I should say repository of exoplanet observations, where amateur astronomers who are doing this kind of differential photometry can store their raw data so that professional astronomers can access that database just as they are with variable star data to be able to do some follow-up science on some of the TESS objects that more than likely will be coming in. And then, of course, off in the distant future is James Webb satellite. There are also some telescopes out on the horizon for doing direct imaging, but those are several years away. So let me, if I could, summarize where we are, open it up for questions, and then if I think we have a few minutes, I'll kind of go into a case study. So just to summarize, hopefully what I've been able to demonstrate is that amateur astronomers can in fact do exoplanet observing. We can also do observing of exo-objects. We can help professional astronomers. And, you know, coming from a deep sky imaging and a planetary imaging background myself, I find it just as challenging, if not more, than, you know, developing a nice image of a nebula or a galaxy, especially given that we can actually be truly contributing to science. Now, let me just say a few words, if I could, about my personal view of the granddaddy of everything, which is direct imaging, and where amateur astronomers can play in that. If you imagine trying to image a dim planet next to a very bright star, there's 3 or 4 things coming into play here. One is the limitations, the diffraction limitations of the telescope. The second is the any limitations based on atmospheric seeing, and the third is the nature of the being able to detect the difference in light between a host star and a planet. With respect to the diffraction limitation issues, that's one of the hardest to overcome. There's some research being done with some interesting ways to what I'll call break the point spread function, but that's probably the toughest. As far as seeing limitations, those of you who may have heard Cliff Ashcroft's presentation, I think a few weeks ago on the imaging channel here, a technique called speckle interferometry is being used to be able to get by amateur astronomers amazing differentiation between 2 binary stars. And in fact, doing some computations on what is possible currently, it is within the realm of possibility to, in terms of looking at exoplanets of, let's say, 5 astronomical units from its host star, if it's large enough to be able to actually detect that exoplanet. However, you then come up against the third problem, which is be able to, with a CCD detector, to be able to detect the change in photons coming into pixels where the planet is versus the huge amount of photons coming in for the host star right next to it. But an interesting sort of set of experiments is currently taking place with something called a charge injection device, which is used in industrial applications, which is, if you can imagine, a CCD detector where you can read out pixels differently and allow some pixels to accumulate differently than others. You can imagine a situation where you can be observing a bright star and sort of limit the photons being collected by the bright star, but allow the photons of the exoplanet next to it to accumulate more. So my personal belief is that, at least in terms of being able to detect a exoplanet next to a host star, maybe not actually imaging it, my personal belief is that maybe a combination of some of these techniques, speckle interferometry, use of CIDs, use of maybe some interesting masks on the aperture of a telescope, that I'm going to be optimistic and say that it might be possible in the future for amateur astronomers to be able to at least detect an exoplanet next to a host star. We're talking about, though, a huge difference in magnitude, and that's where the CID might come into play. All right, well, let me stop there, Adam. Before I go into the case study, some folks may want to depart, others may want to stay on, but let me see if there's any questions anybody has, or if there's some that you have that I can answer.
Yep, there's a few questions popping in. I'll start with the first one that came in. Why not use the check database?
Very good question. So what the question is the check database is the ETD Exoplanet Transit Database, which is it's the best repository right now. It's sponsored by the Czech Astronomical Society. That was where I cut my teeth on exoplanet observing. It's an archive, very excellent archive of amateur astronomer data. And in fact, indeed, the proposal that I'm making to the AAVSO, in fact, is that we combine forces with that database, given the nature of the archive that is there. The only difference is that those of you who are familiar with the ETD database is that for the kind of research science that we need to do here, there needs to be more data stored in the database than what's currently in the ETD database. So although it's a good archive for previous transits, there's a lot more information going forward that we need to store. But very good question. Other questions, Adam?
Yes. Let's see. Do you have software recommendations for analysis of the images, ideally for Mac?
For a Mac, well, the best analysis program, in fact, if you go to my website and you look at the guide that I have a link to there, is called AstroImageJ, which to my knowledge, and somebody out there may correct me, I believe only runs on Windows computers, based on the ImageJ imaging processing software, I think that NIH had developed. I don't know if that's compatible on a Mac, although I suppose if one runs a, hate to say it, but Windows, operating system on a Mac, maybe you could do it. But AstroImageJ is by far the best all-in-one image processing software for exoplanet observations.
Another question. How good does mount tracking have to be? How critical is it that the exact same pixels are used throughout the imaging session? Do you have to guide with PhD? If you guide with PhD, is that going to be good enough?
Okay, good questions. The answer is yes, yes, and yes. The guiding is one of the most important factors. PhD guiding works great. I have an active optics unit, but I've done exoplanet observing without the AO unit, so using PhD guiding, I should say off-axis guiding, not with a guide scope, just because of differential flexure, which will probably be too much for the kind of precision we're doing. As far as keeping it on a given pixel, obviously the better able to do that would be fine, but the kind of guiding I do is I'm within 2 pixels, maybe 2-3 pixels. You don't want it to wander too much, because if it wanders onto a pixel, that is going to cause an artificial change in the ADU counts, then that's obviously something we don't want. But what this does suggest, again, as I sort of alluded to earlier, is the importance of flat fielding. Because you can imagine if the image, if the host star wanders onto a dust mote that hasn't been properly flat fielded, that's going to cause a change in brightness. So flat fielding, guiding, periodic error correction, all that very important.
And Elizabeth Warner is commenting that AstroImageJ does work on Macs.
Oh, good. Thank you, Elizabeth. Elizabeth is with University of Maryland Observatory, and thank you, Elizabeth, for that.
Yep. And the same person is asking, is there example data available to play around with and follow a walkthrough? I don't know if you have it on your website. Someone did post some example data in the comments, or in the comments of this session, but I don't know if you have anything like that on your website or know of anywhere to find it.
I don't, but I did see, in fact, I did try downloading, actually. I forget who the person was that loaded it up on a Google Cloud sort of thing. I couldn't actually download it, so I forget who the person was, maybe they're on the call here, did have a number of images and I think some calibration files and also some sample light curves. So if maybe, Adam, after this session we can figure out who that person was, and then maybe if they're on the call here. And but yeah, that's some good data to try. But if you go to my website again, the guide does walk through in detail. I think in enough detail that you could actually step through a whole observation session and do your own sort of sample data.
Elizabeth Warner would be glad to share her data. So
Okay.
if we needed Elizabeth, I don't know if you know how to contact me on Google Plus, but if so, you can contact me or Dennis via his website, and we'd be glad to share that for anyone that's interested.
Okay.
I'm going to ask my question
Yeah,
because
sure.
Eric got my mind kind of running with this one. We all historical data. One of the things we hear in deep sky astrophotography when we're doing pretty pictures is, why are you shooting that same? What do you get out of it? You know, the Hubble's going to do it better than you, and why are you shooting the same object that you could probably look up and see everyone that's into it has probably shot in the past? And then I think about like a common object and all the stars around that common object, and if there was some sort of repository where we could send all of our calibrated linear data, and then somehow someone would have to design a program, of course, it's easy for me to say, but where they could kind of combine that data. Everything has a FITS stamp, it has the time on it, and there are other stars in the field that would give you a relative brightness. It seems to me like you'd be able to refine out light curves and possibly even not just confirm exoplanets, but possibly discover some if you were using that much data and reducing the noise that much. Is there anything? Does anything like that exist, or?
Very good question. There actually is a grad student from, I think, Rochester, University of Rochester, who in fact is, I've talked to, in fact, the possibility of a automated pipeline that will take images such as what you're suggesting. Now, these would have to be on the same night, let's say over a 4 or 5 hour period.
Right.
Okay. They would take images of an arbitrary star field and imagine doing what a human would do manually, which is pick a star as a candidate host star of an exoplanet, pick a bunch of COM stars, do differential photometry, see if there's a change in light curve, and if not, move on to the next one. So yes, one can imagine a robotic sort of program that would go through a number of images and try to classify them as to which of those host stars is causing a transit to take place. So the answer is yes, theoretically it could be done. There's at least one person I know that has talked about doing such an automated pipeline. I don't know, how far that has advanced, but yes, I would say it's theoretically possible.
Yeah, I was actually, Dennis, this is Eric. I was going to formulate the same question. Adam will tell you that I have a ton of data from dark sites, from a dark site, that could be candidates for just such analysis. I'm looking at M101, in which we have 3 nights sub-arc second observation, with hundreds, if not thousands, of stars in that.
Yeah.
Could be candidates. And to look at one star, I think you would go freaking crazy. But if you could scan that whole image and then sort out the ones that are good candidates, you would have a lot of data to look through for hundreds, if not thousands, of stars. And I think I'd probably have 20 or 30 sets of luminance images to do that on, each with very long exposures.
Well, and furthermore, what I would suggest, even as an approach, as an algorithm for doing that, is to first start doing a small region of interest to see if there's any cumulative light change in that region of interest, and then this is kind of like what Kelp does, and then if there is a change in that region of interest, then sort of hone in on what stars there. So that might be an approach to doing it. So yes, I think it'd be a great PhD thesis for somebody who wants to develop such a program. That's probably actually in honesty, what the professionals use for something like Kepler to detect its light curve. There are citizen scientists out there who are looking visually at light curves, Kepler light curves, to see if they can, visually see a change in star brightness. But I can imagine a automated routine being possible.
Well, I think that if I were to pick out a couple of stars, I would spend hours doing that, but I have a field with thousands of stars on it. So an automated program seems like the only way to reasonably do this. And I'm just one of hundreds of people that have these archives of calibrated data, of calibrated images to do this on.
Right.
There's a wealth of information already out there.
Yeah.
Program to do it.
I agree. Yep.
I have a question, Dennis.
Go ahead, Josh. Sorry.
Is there an optimal sub-exposure time for statistical methods? I know you talked about maybe 8 to 13th magnitude stars, but I mean, some people at dark sites might be taking like 15 to 20-minute subs. Do you need to take a certain amount to kind of sample that time more effectively?
The key thing has to do with the first of all, obviously you don't want to saturate the camera, but more than that, the key thing has to do with being able to get a exposure time where you maximize the SNR, but you have the full width half maximum spread across, let's say, at least 3 pixels. So there's also a question of perhaps binning involved. You don't want to bin too much. So it's a balance between getting the full width half maximum spread across, let's say, 3 pixels, having the best SNR you can, and thirdly, however, not saturating your detector. One of the challenges is, if you can imagine, with the length of time these transits occur, if you start the transit when the star is, let's say, at 25, 30 degrees off the horizon, where you're looking through a lot of air mass, by the time the transit gets over your local meridian, the relative magnitude of the star, or the brightness of the star, has changed so much that we actually have to be careful about the exposure times that are initially set to make sure that by the time it's over the local meridian, it's not saturating the CCD camera. So all these factors go into selecting, the right exposure time.
Dennis, Dennis, I have a question about.
Sorry. Before we get there, my normal rule of thumb is to set the exposure time so that the ADU counts are, let's say, around 20,000 or so.
For the stars.
Yeah, that's for the stars.
I'm sorry?
That's for the stars, because we usually go background ADU count, but I'm sure you're saying for the stars, so you don't want to.
For the star, yes. I'm sorry, the star, so that the star peak ADU count is around 20,000.
Thanks.
Dennis, this is Tolga. How are you?
Hi, Tolga.
I wanted to ask you about linear cameras versus non-linear cameras.
Right.
Maybe that will clarify some of the questions.
So I'm sorry, your question is what?
How do you set the exposure time on a non-linear camera that has a what do you call that? Anti-blooming gate.
Anti-blooming, Tolga. Anti-blooming.
Yes. Anti-blooming gate.
Well,
obviously you want to stay in the linear part of the sensor.
You definitely want to stay in the linear range, and if it is not a linear camera, AstroImage actually does have a facility on, Tolga, if you're familiar with that calibration screen, there is a facility for characterizing the linearity of the camera so that it can make some corrections. But I would say, if at all possible, just stay within the linear range of the camera. Most cameras I'm familiar with, quite frankly, are fairly linear up to about 45,000, 40,000, maybe up to 50,000 ADUs. So I'm not too familiar with many nonlinear cameras being used for this work, but I could be wrong.
Alex is asking an interesting, actually important question. How often is there a good transit target to image? Every night? How often does any given target star have a transit that we could image?
Every night. In fact, if you, again, go to my website, and in that guide that's there, you'll see a link to the this Czech Republic thing that we alluded to earlier. It's a really good site for doing predictions of exoplanets at your latitude and longitude. And every night there's, several exoplanets targets that are available to you. Now, with some of these, research projects going on, like the Hubble thing or the KELT thing, those are only available on certain nights at certain locations. But if you want to get into exoplanet imaging, any clear night, they're out there. And just go to the ETD website, and you'll see, put in your lat long, and it'll show you what exoplanets are observable from your location, the beginning and end transit times, and so on. So, yeah, any night.
Another question, if using a DSLR, should the RGB image be split and use one particular channel, or use the full RGB image?
Well, interesting thing about DSLRs, I am not aware, I hate to say this, of any exoplanet observing using DSLRs. They've all been using CCD monochrome cameras, and for a couple of reasons. One is that that allows for different filters, and in fact, in some of these surveys, it's required that we use standard photometric filters such as Johnson-Cousins or Sloan Deep Sky Survey filters. With a DSLR, I think it would be an interesting experiment for someone to try, maybe binning to get it to be, I don't know if this is, I'm not a DSLR guy, but I know some folks have tried binning color CCD cameras to turn them into monochrome cameras. Resolution is reduced, but it would be an interesting experiment to see if one could do that with a DSLR. So bottom line is, I'm not familiar with any exoplanet observing using a DSLR camera, but it's not to say it can't be done.
Well, that leads kind of nicely into his next question, which is any recommendations for an entry-level CCD camera for this kind of work?
Yeah, I would say that, probably even some of the low-end ones might be okay. I mean, I have a Starlight Express 694 monochrome myself. It's, not a super expensive. It's probably in the moderate, medium range in terms of price. But, it wouldn't be out of the question to try someone wanted to try a, Orion G3 monochrome camera. It probably will be okay. It's probably gonna have more noise, maybe not, not as good in terms of, maybe a lot more dark current, but all of those can be calibrated out. So yeah, I would say if somebody's got a, what I'll call a low-end CCD camera, I'd say give it a try. Again, it's just counting photons is all we're doing.
Dennis, what are the odds for any star for any 6-hour period having a transit?
I'm sorry, say again?
What are the odds for any 6-hour period for any particular star having a transit?
Probably 1 in 1,000. I don't know. You mean randomly picking a star and looking at it?
You have a star field with 2,000 stars on it.
Yeah. Well, think of this. Think of the factors involved. First of all, it's got to be a transit that's in our line of sight, and in fact, not only in our line of sight, but within a few degrees inclination of our line of sight. So that probably is the biggest factor in terms of reducing the probability of what stars would be able to have a transiting planet. First of all, most stars have planets transiting them, or have planets going around them. Let's just say that. So it's really which stars have planets transiting them that are in our line of sight. Number one. Number two, that those planets are hot Jupiters. That's to say, close to the star and large. So all of those factors play into, what the probability is. I don't know, but probably, I don't know, 1 in 1,000, maybe. I don't know.
That kind of touches on one of my questions as well, which is based on something you said early on in the talk. First of all, you're mostly looking for hot Jupiters because they give you fast enough transits that you'd be able to record it in one night of imaging. But you also said that you said 1 in 5 stars have planets, and I recently read an article that claimed every star has a planet.
No. I think I said 1 in 5 have probably Earth-size planets.
Earth-size. Okay. That's where I was confused there.
Yeah.
So basically, they're out there. It's just we're looking for a particular type. We're looking for the detectable planets. We're looking for the ones that we could possibly see.
Right.
So that I think kind of dovetails with Eric's question. How many out there? Well, it's not how many out there. It's more how many out there that are detectable.
Right. Now, as I think we amateurs evolve into more sophisticated detection techniques, such as radio velocity, we need a pretty good high precision spectrograph to do that, but there are some on the market that might be possible to use. Secondly, microlensing. I think we can have some ability to do that, but the microlensing approach requires an observation to be done within a very small time frame, because if you can imagine, if you're looking toward the middle of the Milky Way and that planetary system is moving in front of a background star, that transit of that entire planetary system is on the order of maybe a few weeks or something. So if there was a coordinated way in which professional astronomers could alert us amateurs that there's a microlensing event taking place, we could perhaps hone in on that particular star. And because if you recall from the dip in that the light of that microlens is pretty deep, so we might be able to do a microlens detection.
Awesome. And you even seem to be caught up with the questions. So.
Okay. Let me just quickly, I know it's getting late, but I'm just going to cycle through quickly a couple of slides on a case study and then see if there's any final questions. By the way, this presentation, I should have mentioned at the beginning, is also available on my website, and you see different references there. So this is that star I mentioned at the very beginning. This is sort of the field of view of the image I took of it, and that is the particular host star WASP-12, which generated that particular light curve you see. This was done here in my backyard observatory with what you see here. The exposure time was 45 seconds, 337 exposures. This is my setup, typical deep sky thing. I do have, as I said, active optics, which isn't necessary, but have an off-axis guide camera, Lodestar X2, monochrome CCD camera, filter wheel, and everything is remoted indoors. Let me just say a few words about, I won't go through all of these phases. There's a couple of key points I want to make. These phases are very, very familiar to anybody who's done deep sky imaging, except for a couple of key things. And let me just quickly go to this. This is the importance of flat fielding. If you imagine you're looking at a star in the lower right field, let's say, prior to a meridian flip, and then once the meridian flip happens, that star is going to all of a sudden, if you don't rotate the camera, going to end up on a dust mote, and that's going to cause a change, artificial change in the light curve. Now that can be corrected, as we'll see in a minute, but this is the importance of flat fielding. This is a image, sort of a blown up image of this differential photometry, and the way it works is you put a aperture around the host star, which is sort of the middle circle, and then a donut around the background area around the star, leaving a little gap in between. And what happens is, for each star, the host star and the comparison stars, because the brightness of that star includes the background light, which there always is, the first thing that happens is the flux of that host star has subtracted out of it the background brightness or the background flux. So that's the first thing that happens. And so this is done for, in this case, the target star, which is T1, and in this field of view for this case study, the other comparison stars. And what you do is you plot that, and what you get is this. The blue dots are the original observation points. The red dots with the line going through it is the transit model fit to it, which you see is a pretty good fit. The next line is the RMS errors between the model and the observed data. And then the other three are the comparison stars. You can see that the comparison stars are relatively stable as opposed to the host star. And so that's indicative of, in fact, that we don't have a variable star as a comparison star, which would be a disaster. So this shows that everything looks copacetic. The bottom is a plot of the sort of blue curve is the air mass, predicted air mass, and then the little brown curve underneath it are the observed total ADU counts of the comparison stars, and you see how they track almost perfectly the air mass. The reason for that graph is if there's any passing clouds, what you will see is a change in the brown curve, that is to say the total ADU counts, which isn't a disaster because, again, they're all decreasing, including the target star, but it just gives you a feel for how good the observation is. This is just an example of what comes out of the analysis. And finally, this is the comparison of the model fit I did versus published for all the different parameters. And you can see that, I'm within 90% plus accuracy of published data. But again, this is in moderately light polluted skies in a suburban location with a moderate sized aperture. And finally, this is an example of where a meridian flip had occurred. The blue dots, all of a sudden you see changed arbitrarily or artificially because of the flat fielding effects. But this particular analysis software, AstroMSJ, corrects them as you see with the red dots. So that's it as far as the presentation. Again, it's on the website. And Adam, let me just turn it over to you and see if there's any other questions.
I don't see any questions currently, but if you guys out there do have any further questions, please type them in now. Yeah, it's interesting. I keep dwelling on, I think, what Eric was asking about historical data and getting it automated. And if that grad student, hopefully he doesn't. Hopefully this is either his thesis or he doesn't graduate so quickly.
Yeah.
Because it really, I mean, it's obviously dependent on processing ability. But even just if you, I'm not sure, I haven't used AstroImage J, but even if you could use that as kind of an engine that you could automatically feed the data into, it'd be interesting. I
Yeah.
mean, the more data, the more you're just working out the noise, and you can
Yeah.
really dig down and get some really slight tips, I'm sure, from that.
Yeah.
You know, I think that we have lots of good data. The difference between, I think, what we collect and what you show on your example is that we do extended exposures, 10, 15, 30-minute exposures, where you do a series of short exposures. So in a particular night, we're not going to have a lot of data points.
Yeah, the other problem I fear is that with deep sky imaging, you're not too concerned about saturating individual stars, whereas, it's critical, obviously, that the target star not be saturated because you'd be losing photons being collected. So I think that's the other possible problem is that using regular, deep sky imaging pictures or images is that there could be a lot of stars that themselves are saturated in the field.
Well, actually, I just looked. I have a data set up here. I was looking at it as you were talking. And even though there are a handful of saturated stars, there are literally hundreds that are not.
Yeah.
That's kind of
very nicely.
That's kind of what I was thinking. In a field of 2,000 stars, you're going to have a lot of dimmer stars in there. I mean, maybe you're only going to have 100 or 200 candidate stars, but it's still stars in most likely a popular field that lots of people have shot. The time issue could be a stronger issue because, yeah, we're shooting over 10 minutes when optimally it'd be good to get a reading every 3 minutes. But at the same time, the volume of data that would be available, you'd almost be able to work through that.
Right. Yeah. No, it clearly could be done. It's just a matter of somebody writing automated software to do it.
Oh, I wish I didn't have a job. Really cool presentation. It's amazing what amateurs are doing these days.
Yeah. Okay. Any other questions then?
I don't see any further questions, and I see a few people dropping out of the room, but I do first want to...
I did have a question.
I'm sorry, go ahead, Alex.
This is a good thing to do on a moonlit night, too, right?
In fact, this example that I'm showing here, this case study, was done, this particular star was within, I think, like 20 degrees of a full moon.
Okay.
Again, because we're compensating for the background sky glow, and it's all relative between the comparison stars and the target star.
You actually select the comparison stars in Image J?
Yes, you do. Now, it's a little bit more scientific than just randomly selecting what at least for the Hubble program, and in fact in general, one can go to the AAVSO website and for a given field of view, take a look at known what are called sequence stars. That is to say, stars that are non-variable, because you obviously don't want to select a comparison star that itself is variable, otherwise it'll throw everything off. So the AAVSO website is a good source for a given field of view determining what stars are not variable and in fact have well-defined characteristics. One of the selections, in fact, if you go to my guide, you'll see best practices there for selecting the COM stars in that they should be within half to 1.5 magnitude of the target star and also of the same spectral type. The reason for the same spectral type is because as you're looking at these long transits through changing air mass, stars of different spectral type are going to change differently in terms of their brightness, and so you want to make sure that you have as close in the spectral type of the comparison stars to the host star as well.
Interesting. Awesome. Okay.
Well, in that case, I have one more comment. If that's the case, then perhaps you want to look at an exposure of a particular color filter. That eliminates that issue, doesn't it?
I'm sorry, it was a little garbled. Say again, or maybe Adam can repeat
Well,
it.
if you look at it in an RG or B filter, you're automatically selecting for those stars of a certain color, and those wavelengths of light are going to be absorbed by the air mass the same from star to star, and you don't have an issue of luminosity versus color, of differential absorption.
Yeah, I think what you said, if you're using an RGB camera, that it'll compensate for. Is that what you said?
No. He's asking if you use either an RG or B filter with a monochrome camera, whether it would compensate for that.
Oh, I see. Well, it will compensate for. I don't know if it will I think it depends on the difference in the spectral type and whether it's a blue or red comparison star. I think the general rule of thumb would be just try to get it as close as possible. But even if not, what Astro MSJ is able to do is it's able to detrend certain characteristics to take care of that. So it's not completely completely out of the question that Astro MSJ can't compensate for some things. Any other questions?
Hold on. Oh, you got it. The moony nights. That was Alex's question. That seems to be all the questions. Dennis, first of all, thank you for coming on. That was a great presentation. I hope you get a few candidates from viewers here that might be able to contribute. And interesting that you mentioned that you get published in the paper with Hubble if your data is used. It sounds like a real honor to have that occur.
Well, in fact, Tolga, who was on earlier, and some of the other folks from AAI in New Jersey, they're going to be have their names as co-authors on one of the first papers.
Really cool. We'll congratulate Tolga when it happens, but that's definitely something we should all be so lucky or strive to do.
Yeah.
All right, well, thank you very much, guys. Next week, Josh is going to be on presenting a new format for us, the making of an image. And whenever we come across an awesome image that that image of the week may not go far enough to recognize and something we really want to hear what went into it, we might invite the people on to speak about their image for a while. And Josh took the Cat's Eye Nebula image, and he put a combined, I think, 130 hours into it, maybe longer than that. And he'll be on speaking about it next week, and to hear a little bit about what went into it, acquisition and processing-wise. But again, I do want to thank Dennis for coming on, and well, I guess we will see you next week. Thanks a lot for coming, guys.
All right. Good night.
Hey, Dennis, a great presentation. Well,